Here's another example. Let's say we want to find the most general function f of x for which x squared times the derivative of f of x is 3 times the original function f of x. Well, step 1, we turn f prime of x into dy dx and f of x into just y. And can it be separated? Yes. We're going to have to divide both sides by y and get dy over y. And see, we bring the dx up, so we get 3 dx, and we have to divide both sides by x squared, and we get this. Little bit unpleasant, but it's possible. Then we integrate both sides, and what do we get? Over here, 1 over y dy is the natural log of the absolute value of y. Over here, plus c, but we're going to put the c over to the other side like we did in the last example. This is integral of 3x to the minus 2 dx. So we raise the exponent by 1 to get negative 1. So we get 3x to the negative 1 over negative 1 plus its constant and the constant from the other side brought together. So we get the natural log of the absolute value of y is minus 3 over x plus some constant, which might be nicer to write c minus 3 over x, so we don't have it save on a symbol. Let's see, we have to solve for y. We have to raise both sides to the e. So we get the absolute value of y is e to the c minus 3 over x. And so y is plus or minus e to the c minus 3 over x. And this is a trick that we're going to do in the future. We're going to call this plus or minus e to the c times e to the minus 3 over x. And what has gone wrong? What has gone wrong? Over here, when I went from here to here, I divided both sides by y. That can only be done if y is not 0. If your original function, the function that you're looking for, is not 0. And here we say, well, wait a second. If y equals f of x is 0, this works. In fact, this is the function that the very first differential equation we had in the very first video, and we talked about how being 0 works. So what it means is y is plus or minus e to the c times e to the minus 3x, or y is just straight up 0. And we're going to do this trick a bunch more times, and that's why I'm talking about it, but e to the c is any positive number. E to the c, here's the graph of e to the x, y equals e to the x. You see that you can hit any positive number in that fashion. And plus or minus gives you all the minuses, and being 0, that basically means that y can be a e to the minus 3 over x, where a is any real number. And I don't like writing all that out, so I can just say a is in the real numbers. And hopefully I can start using that alone. But if a is a positive number, then we're talking about plus e to the c is the a. If a is a negative number, we're using the negative, and if a is 0, we're using this, which multiplies by that to get just 0. So this is what we call the most general solution to the equation. And let's try it. What is our original equation? X squared f prime of x equals 3f of x. The question is, you don't have to verify all your things, but it's a really good habit. The question is f prime of x times x squared really equal to 3 times f of x? Well, what is the derivative? If f of x is a e to the minus 3 over x, then the derivative is, leave the constant out front, e to the something is e to the something, that's not a 2, that's an x, e to the minus 3 over x times the derivative of what's inside, and the derivative of minus 3 over x is, that's 3x to the negative 1, so that becomes positive 3x to the minus 2, which is a e to the minus 3 over x times 3 over x squared. And so this is what we're trying to test. And so f prime of x times x squared is ae to the minus 3. Why does I keep turning it into 2's? 3 over x. A to the a times e to the minus 3 over x times 3 over x squared. That's the derivative. Multiply that by x squared. And these x squareds go away. And that is, in fact, 3 times ae to the minus 3 over x, which is 3 times f of x. In conclusion, yes. If f of x is this thing, then its derivative times x squared is 3 times the original function. Its derivative times x squared is 3 times the original function. Yay! We've solved a separable differential equation. And let's move on to more complicated ones.